So let's start the final lecture of number theory. So in this lecture, we will see remaining all syllabus in short. So already we have seen fundamental theorem of arithmetic. Then we have seen linear congruences. So congruence relation already we have seen. So up till Chinese remainder theorem we have seen in offline mode. So next, that is Chinese remainder theorem. So what is Chinese remainder theorem? Let n1, n2 up to nr be positive integers such that GCD of ni and nj equal to 1 for I not equal to j. Then the system of linear congruences Ax congruent to A1 modulo n1, x is congruent to A2 modulo n2 up to x is congruent to AR modulo nr. So this is system of R linear congruences. So this system has simultaneous solution which is unique modulo the integer n1 into n2 up to nr, that is n. So this system has unique solution. So it gives, this solution is given by Chinese remainder theorem. So this is statement of Chinese remainder theorem. So its proof is there, but we skip. So you can do these examples at home. So you can solve this linear congruence 25x congruent to 15 modulo 29. So already we have seen this method. See. So first you have to find GCD of 15 and 29. If it divides 25, then this linear congruence has solution. If it does not divide, then this linear congruence has no solution. So you can use that theory and you will solve these three examples. So you can do it at home. So next chapter, that is Fermat's theorem, chapter number 4. So in that there is first Fermat's factorization method. So instead of its theoretical part, so directly we'll solve one example. So clearly you'll understand what is Fermat's factorization method. See, so for example, factorize 10,541 by Fermat's factorization method. So what you have to do? So you have to find two integers whose square are in between. Yes, square of these two integers, this integer n should lie. So 10 square. So these two integers should be consecutive integers. If suppose this is integer k, then this integer should be k plus 1. So k plus 1 square and k square. So these are two squares of these integers. So this integer n should lie between these two squares. So it should lie between square and k plus 1 square. So you have to find such two integers. See, means you have to find such integer k which satisfy this condition. Which condition? So n should strictly less than k plus 1 square and strictly greater than k square. So you have to find this integer k. So you have to find k such that it should satisfy this condition. So here for n equal to 10,541, so k is equal to 102, so which satisfy this condition. So this we have considered the value of here k square minus 10,541 for k greater than equal to 103. So here we are taking values of k from 103 to 104, 105 and likewise. So we will consider this difference k square minus 10,541. So for k equal to 103 it will be 68. You can check for k equal to. So here we are taking k equal to 103. So here we are taking k equal to 104. Here we are taking k equal to 105. You have to continue this process. Let us see, you are finding here difference 104 square minus 10,541. So that is equal to 275. You have to continue this process until you are getting complete square. So 275. So this is not complete square of other integer. So it is also called perfect square. If you take k equal to 105, see, so you'll get, just a minute. Yeah. If we take k equal to 105, so this difference will be equal to 484, and 484 is square of 22 square. So when you are getting square of any integer, so you'll stop here. So in that case, so what we'll get, you'll get 105 square minus 10,541 will be equal to 22 square. So I will write 10,541 as 105 square minus 22 square, or using this formula, that is a square minus b square equal to a minus b, or a plus b into a minus b. Simply we are using this formula and we will get this. See, so that is equal to 127 multiplied by 87. So we write 10,541 as 127 into 40, 83, sorry. So this is the Fermat's factorization of 10,541. So this is Fermat's factorization method. Very simple. You can use this method to find Fermat's factorization of any integer. So you can do these two examples at home as a homework, and you can check answers. So for 2279, Fermat's factorization will be 89 multiplied by 23, and for this integer, so would 119143, so this will be 421 into 283. So check this, so you can do it at home. So next theorem, that is Fermat's little theorems, or this theorem just called Fermat's theorem, Fermat's little theorem, or just Fermat's theorem. Fermat's theorem. See, so what is statement of Fermat's theorem? Actually, statement is very important. So this statement of Fermat's theorem: if p is prime and p does not divide a, so p is a prime number and that prime number does not divide a, then p minus 1th power of a will be congruent to 1 modulo p. So a is any integer. So in that case, a raised to p minus 1 will be always congruent to 1 modulo p. So there is one famous corollary. So that corollary is called corollary to Fermat's theorem. So what is statement of this corollary? So this is well-known corollary. Corollary to Fermat's theorem. So what is statement of this corollary? A raised to p. If p is a prime, then a raised to p is congruent to a modulo p. It is not necessary. P does not divide a. Still, this statement is true. So either p divides a or p does not divide a, then again this statement will be true. So in both cases. See. So this is statement of corollary to Fermat's theorem. So next lemma, if P and Q are two distinct primes, says that A raised to P is congruent to A modulo Q and A raised to Q is congruent to A modulo P, then A raised to P into Q will be congruent to A modulo P into Q. See, P and Q are two distinct primes, says that. So A raised to P is congruent to A modulo Q and A raised to Q is congruent to A modulo P, then A raised to P into Q congruent to A modulo P into Q. See. So definition, see, you can use this lemma to solve problems. Its proof is there, but we'll skip this. So next definition, that is pseudo prime. What is pseudo prime? See, a composite integer n is said to be pseudo prime whenever n divides to the n minus 2. So n is called pseudo prime if satisfies this relation. So alternately, you can write this relation in the form C, that is 2 raised to n is congruent to 2 modulo n, means n divides 2 raised to n minus 2. So n is called pseudo prime if that n satisfies this relation, that is 2 raised to n is congruent to 2 modulo n, So there are infinitely many pseudo-primes. So what is the first value of n which satisfies this congruence relation? So that first value, that is smallest four integers which satisfy this relation are, see, first that is 341. 341 is not prime number. So these are non-prime numbers which satisfy this relation. So second, next integer to 341 which satisfies this congruence relation is 561, 645, then 1105. So these are, see, first four pseudo prime numbers. There are infinitely many pseudo primes, and so pseudo primes are rarely exist than prime numbers. So up to 1000 there are only three pseudo primes. So first pseudo prime is 341, second pseudo prime is 561, and third pseudo prime is 645. So as compared to regular primes, so pseudo primes exist rarely. So their number is smaller. So there is example, find the remainder when 2 raised to 50 is divided by 7. So here we'll use Fermat's little theorem to find remainder when 2 raised to 50 is divided by 7. So let us take a equal to 2, p equal to 7 in Fermat's theorem. So you'll get this congruence relation. See, that is 2 raised to 6 will be congruent to 1 modulo 7. So here we are putting p equal to 7, a equal to 2. So taking 8 power of both sides, so you'll get 2 raised to 48 is congruent to 1 modulo 7. See, so multiplying both sides of this congruence relation by 2 square, so you'll get 2 raised to 50 is congruent to 4 modulo 7. So it implies that 7 divides 2 raised to 50 minus 4, or you will write, see, 2 raised to 50 minus 4 is equal to 7 into k for some k, for some integer. So for some k belongs to z, you'll write 2 raised to 50 minus 4 equal to 7 into k, or 2 raised to 50 is equal to 7k plus 4. So what is the meaning of this? When we divide 2 raised to 50 by 7, then remainder is 4 using division algorithm. See, so using division algorithm, if we divide 2 raised to 50 by 7, then remainder is 4. So this is our solution. When 2 raised to 50 is divided by 7, then remainder is 4. So next example, to that 5 raised to 38 is congruent to 4 modulo 11. So again you can take a equal to 5, p equal to 11 in Fermat's theorem. So using that you will get, see, you will get 5 raised to 10 is congruent to 1 modulo 11. So taking third power of both sides, you will get 5 raised to 30 is congruent to 1 modulo 11. So let us call this equation as 1. So now, see, so 5 square is equal to 25. So 25 is congruent to 3 modulo 11. So what is 25 minus 3? So that will be 22. So 22 is congruent to, sorry, 11 divides 22. So naturally you can observe 25 is congruent to 3 modulo 11. Or you'll get, so that is 5 square is congruent to 3 modulo 11. So I'm squaring both sides, so that will imply 5 raised to 4 will be congruent to 3 square modulo 11. See, so what is 3 square? That is 9. So 5 raised to 4 will be congruent to 9 modulo 11, or that will imply 5 raised to 8. So again squaring both sides, so you'll get 5 raised to 8 is congruent to 9 square modulo 11, or that will imply 5 raised to 8 is congruent to 81 modulo 11. But what is 81? So 81 is congruent to what modulo 11? If we divide 81, then what is remainder? See, that is 77. So naturally 81 is congruent to 4 modulo 11. So 81 minus 4 is 77, and 11 divides 7. So naturally 5 raised to 8 is congruent to 4 modulo 11. So from equation number 1 and 2, so what we will get? Just you are multiplying equation number 1 and 2, so you will get 5 raised to 38. So what is equation number 1? See, equation number 1 is 5 raised to 30 is congruent to 1 modulo 11. That is equation number 1. And what is second equation? 5 raised to 8 is congruent to 4 modulo 11. So that is equation number 2. So multiplying these two equations, so what we'll get? 5 raised to 30 into 5 raised to 8. That is 5 raised to 38. See, will be congruent to 4 modulo 11. So this is solution of this problem. So next theorem, that is Wilson's theorem. What is statement of Wilson's theorem? Let us see. If p is prime number, then p minus 1 factorial is congruent to minus 1 modulo phi. Sorry, minus 1 modulo p. So see, so this is statement of Wilson's theorem. Yeah. If p is a prime, then p minus 1 factorial is congruent to minus 1 modulo p. So we'll solve some problems on this. So find the remainder when 15 factorial is divided by 17. So since p is equal to 17 is a prime number, so therefore in Wilson's theorem, what we'll get? So p minus 1 factorial, that is 17 minus 1 factorial, that is 16 factorial is congruent to minus 1 modulo 17. So use Wilson's theorem. So here put p equal to 17 in Wilson's theorem. So you'll get 16 factorial is congruent to minus 1 modulo 17. So multiplying, or sorry, so you'll write 16 factorial. What is n factorial? So n factorial is equal to n into n minus 1 factorial. So this formula of factorial or property of factorial. So you'll get 16 factorial as 16 into 16 minus 1 factorial, that is 15 factorial congruent to minus 1 modulo 17. So again minus 1. What is minus 1? So minus 1 is congruent to 16 modulo 17, because minus 1 minus 16, that is minus 17. So 17 divides minus 17. So we can replace minus 1 by 16, because minus 1 is congruent to 16 modulo 17. So that will imply, and you can cancel the 16 to both sides, because GCD of, so what is GCD of 16 and 17? GCD of 16 and 17 is equal to 1. So therefore we can cancel the 16 to both sides. So that will imply 15 factorial is congruent to 1 modulo 17. What is our problem? Our problem is that you have to find remainder when 15 factorial is divided by 17. So here 17 divides 15 factorial minus 1, or you can write 15 factorial minus 1 equal to 17 into k for sum k belongs to z. So z is integer, set of integers. So that will imply 15 factorial is equal to 17k plus 1. It means that, see, 1 is remainder when 15 factorial is divided by 17. So this solution of this problem. So you can do another example, that is 2. Find remainder when 2 into 26 factorial is divided by 26. So it is for homework, so you can do it at home. So next chapter, that is number theoretic functions. So there are some number theoretic functions. So these are not your regular functions. These are number theoretic functions. So first number theoretic function, that is function tau. So what is tau? See, so given the positive integer n, tau n denotes the number of positive divisors of n. The number of positive divisors of n is nothing but tau n. So what is tau n? Tau n is nothing but number of positive divisors of n is called tau n. So for n equal to 12, the positive divisors of 12, so you can list the positive divisors of 12. So these are 1, 2, 3, 4, 6 and 12. So there are total 6 number of divisors, positive divisors of 12, and therefore 12 will be 6. So you can observe. Similarly, what is tau1? So there is only one divisor to 1, so therefore tau1 will be 1. So for 2, tau2 will be 2 because there are two divisors, 1 and 2. See. So for 3, again there are only two divisors, that is 1 and 3. So therefore number of divisors, positive divisors of 3 is 2, and therefore tau3 will be 2. And similarly for tau4, what are the positive divisors of 4? These are 1, 2 and 4. So therefore tau4 will be 3. Similarly tau5. So again there are only two divisors, positive divisors for 5, and therefore tau5 will be 2. And in similar way you can find 2 of remaining integers. So note that if n is prime number, then what is tau n? So tau n will be 2, always 2. If n is prime number, then tau n is always 2. So that will be one property of this number theoretic function tau. So you can write it as a property or a remark. So note that if p is prime number, then tau n is equal to 2. So next number theoretic function, that is number theoretic function tau or sigma. So given positive integer n, sigma n denotes the sum of positive divisors of n. So what is sigma n? See, sum of positive divisors of n. So first you have to find total positive divisors of n, then simply you have to add these positive divisors and directly you will get sigma n. That is summation of all positive divisors of n. So for example, if we take n equal to 12, the positive divisors of 12 are, just we have listed these divisors above in above example. So these are 1, 2, 3, 4, 6 and 12. So if you add all the divisors, so you'll get that is 1 plus 2 plus 3 plus 4 plus 6 plus 12. So that is equal to 28. So sigma 12 will be 28. Addition of all positive divisors of that integer is nothing but sigma of that integer. So this is second number theoretic function, and in similar way, so you can find sigma 1. There is only one divisor, that is 1, and so naturally sigma 1 will be 1. Sigma 2, so there are two divisors, 1 and 2. So therefore 1 plus 2 will be equal to 3. See, sigma 3. So again there are only two divisors of 3, that is 1 and 3, and 1 plus 3 equal to 4, and therefore sigma 3 will be 4. So in similar way, there are how many divisors of 4? So these are 1, 2 and 4. So 1 plus 2 plus 4, that will be 7, and similarly 6 sigma 5. So again you can observe, see, something for prime numbers. If n is prime number, then what is sigma n? Sigma n will be n plus 1 because naturally there are only two positive divisors for prime number, that is that prime number itself and 1, and therefore sigma n will be n plus 1. Sigma n equal to, so alternately you can write, see, so this will be alternate definitions of these two number theoretic functions sigma n and tau n. So you can write tau n as summation 1 where d divides n. If d is the divisor of n, means if there is one divisor, then you will take 1 in that summation. So number of divisors, so this is summation of number of divisors of n, and it is nothing but tau n. Here, see, if d divides n, then you are taking that d in summation. See, means you are simply adding all divisors, positive divisors of n, and you get sigma n. So this is addition of all divisors of n, and this is just number of divisors of n. So next, there is theorem. It is nothing but formula to calculate sigma n and tau n for any integer if here its prime factorization. So if n equal to p1 raised to k1, p2 raised to k2 up to pr raised to kr, is the prime factorization of n is strictly greater than one integer, then what is tau n? So tau n is nothing but, see, in tau n we are just taking powers of these primes in prime factorization. So k1 plus 1 into k2 plus 1 into up to kr plus 1. So this multiplication is nothing but sigma tau n, and what is sigma n? Sigma n is equal to p1 raised to k1 plus 1 minus 1 divided by p1 minus 1 into p2 raised to k2 plus 1 minus 1 divided by p2 minus 1 up to pr raised to kr plus 1 minus 1 divided by pr minus 1. So this is multiplication of these ratios. So there are r ratios. हेलो, हाँ बोला, क्या प्रॉब्लम है? कसली 7 तारीख आहे म्हणजे? तर एक्झामची तारीख तुला माहिती असेल ना? ते भरलं असेल ना तू ऑनलाईन ऑफलाईनचं ऑप्शन? हो मग ठीक आहे ना. So these are the formulae to calculate tau n and sigma n in any situation. Means if you have just prime factorization of that integer, then you can find tau n and sigma n using that prime factorization. Let us see. So next definition, that is definition of multiplicative function. A number theoretic function f is said to be multiplicative if it satisfies this condition. That is, f of m into n should be equal to f of m into f of n. So whenever, so GCD of m and n equal to 1. So if GCD of m and n equal to 1, so f of m into n should be equal to fm into fn. Then that function f is called multiplicative function. See, so there are some theorems regarding multiplicative function. See, the first theorem, the functions tau and sigma are both multiplicative functions. It means both the sigma and tau satisfy this condition. That is, tau of m into n. See, tau of m into n equal to tau of m and tau of n. Similarly, sigma of m into n is equal to sigma m into sigma n. So here, GCD of m and n should be equal to 1. So both sigma and tau are multiplicative functions. If f is multiplicative function and capital F is defined by, so there are two functions, small f and capital F. These are two functions. Small f is multiplicative function and capital F is given by in terms of small f. So this is capital F function. So capital F of n equal to summation of small f d, where d divides n. Then f is also multiplicative function. So if small f is multiplicative, means this function, if small f is multiplicative, then capital F will be multiplicative function. See, so let's take one example. Find the value of tau of 180 and sigma of 180. So let us see. First you have to use, see, just you have to find prime factorization of 180. If you have prime factorization of 180, so directly using last theorem, you'll find sigma n and tau n. So first just find prime factorization. So let's take n equal to 180. So you can write 180 as 2 into 90. So divide it by 2. So again divide 90 by 2. So you'll get 2 into 2 into 45. See, so it will be prime factorization of 180. So 180 you will write 2 square into 3 square into 5 raised to 1. So this is prime factorization of 180. So just you have to use previous theorem. So here, see, means that, what is that? So that is equal to p1 raised to k1, p2 raised to k2, and p3 raised to k3. So use previous theorem for k1 equal to 1, 2, k2 is equal to 2, and k3 equal to 1, and p1 equal to 2, p2 equal to 3, and p3 equal to 5. So you'll get tau n. What is tau 180? That is k1 plus 1 plus into k2 plus 1 into k3 plus 1. See, it will be 2 plus 1 into 2 plus 1 into 1 plus 1, and that will be 3 into 3 plus into 2, and which is nothing but 18. So tau 180. So there are total how many divisors? Positive divisors for 180. So these are 18. So directly you'll find using this formula. And similarly, what is sigma 180? So it will be, so formula is p1 raised to k1 plus 1 minus 1 divided by p1 minus 1 into up to p3 raised to k3 plus 1 minus 1 divided by p3 minus 1. So let us put this value. So you will get, see, 2 raised to 3 minus 1 divided by 2 minus 1, 3 raised to 3 minus 1 divided by 3 minus 1, and 5 square minus 1 divided by 5 minus 1. So it is 8 minus 1 divided by 1, 27 minus 1 divided by 2, and 25 minus 1 divided by 4. So it is nothing but 7 into 13 into 6, and that is 546. So see, what is sigma 180? That is 546, and 2 180 will be 18. So at home you can do this example, so you can find, you can take more, you can find sigma into for these integers, or also you can find for more integers. So that depends on you. So next topic, that is Mobius function. What is Mobius function? This is third number theoretic function. Mobius function is a new mu. So mu is number theoretic function. This third number theoretic function. So for positive integer n, we define mu by the rules mu of n equal to. So let us see what is definition of mu function. So mu of n is defined by, if n equal to 1 means mu of 1 is equal to 1. If p square divides n means, see, power of any prime number, if divides n, then naturally mu of n will be 0. Means if there is repetition of prime number in prime factorization of n, then naturally its mu of n will be 0. And if it is just distinct, so it's prime factorization, if there are no repetition of prime numbers, so in that case you'll write it is equal to minus 1 raised to r, where what is r? R is number of prime numbers in that prime factorization. If there are r distinct primes, means n is just product of r distinct primes, then what is mu of n? So it will be minus 1 raised to r, where pi are distinct prime numbers. So you can see, so here the function mu is called Mobius mu function. So this is definition of mu function. This is third number theoretic function. So for example, if we take n equal to 30, so what is n? See, if n equal to 30, so you write 30 as 2 into 3 into 5. So this prime factorization of 30, and all these three primes are distinct primes. So naturally that will imply, what is mu of 30? So it will be minus 1 raised to 3, because r is equal to 3 here, and which is nothing but minus 1. So mu of 30 will be minus 1. So in particular, see, if n equal to 1, so mu of 1 equal to 1. If mu equal to 2, so here just one single prime. So 2 is prime, and so in that case it will be minus 1 raised to 1, because number of primes is 1. So therefore it is minus 1. If n equal to 3, so 3 is prime number. So again it is minus 1 raised to 1. So it is minus 1. So if you take n equal to 4, then what happens? If n equal to 4, we'll write 4 as 2 square, and there is repetition of prime, means 2 square. 2 is prime, 2 square divides 4, and therefore naturally in that case mu of 4 will be 0. So mu of 5 is minus 1, you can check. So 6 you can write 2 into 3. You write n as but product of two distinct primes. So mu of 6 will be minus 1 square, and that is plus 1. Mu of 7 is equal to minus 1, and likewise you can check. So again here you can observe that if p is prime, then mu of p equal to minus 1. Second, mu of p raised to k is equal to 0 for k equal to 2, or sorry, k equal to 2 or greater than equal to 2. Means there is repetition of prime, then naturally mu of p raised to k will be 0. The function mu is multiplicative function. So again, it will satisfy mu of m into n will be equal to mu of m into mu of n. See, where GCD of m and n equal to 1. So this one property of mu function. For each positive integer, so another property of this mu function, for each positive integer n greater than equal to 1, what is summation of mu of d? See, where d divides n. So what is addition of all mu of d? Where d is divisor of n. So it is equal to 1 if n equal to 1, and this is equal to 0 if n is greater than 1. Means mu of all divisors of n is always 0. Summation of mu of d for all divisors d of n. So this quantity is always 0, where d runs through the positive divisors of n. And next, that is Mobius inversion formula. So this important formula, important theorem. Actually, its proof is there, but we skip this proof. Yeah. See, let f, capital F and small f be two number theoretic functions related by the formula. Capital F of n is given by summation of small f of d, where d divides n. Then what is small f? So what we have given? We have given capital F in terms of small f. We write capital F in terms of small f. Then how to write small f in terms of capital F? So it is given by Mobius inversion formula. That's why this formula is called inversion formula. So small f of n equal to summation mu of d, capital F of n upon d, where d divides n, d is divisor of n. Or also you can write summation mu of n upon d into capital F of d, where d divides n. So this is statement of Mobius inversion formula. See, so next there is one theorem. If capital F is multiplicative function, then small f is also multiplicative function. Means if capital F satisfies this condition, that is small capital F of small m into n equal to capital F of small m into n is equal to capital F of small m into capital F of small n, implies that small f of m into n is equal to small f of m into small f of n, where m GCD of m and n equal to 1. So this one property. So this is about Mobius inversion function and Mobius inversion formula. So next chapter, that is chapter number 6, Euler generalization of Fermat's theorem. So in that we will see Euler's phi function. What is the definition of Euler's phi function? So Euler's phi function, that is phi. So this is Euler's phi function for n greater than equal to 1. So let phi n denote the number of positive divisor integers. So what is phi n? Phi n denote the number of positive integers not exceeding n, that are relatively prime to n. Means so number of positive integers which are strictly less than n and which are relatively prime to n. So that number is nothing but phi of n. The function phi is called Euler's phi function. So for example, if you take n equal to 30, then the integers, see, relatively prime to 30 and less than 30 are 1, 7, 11, 13, 17, 19, 23 and 29. So therefore, there are total 1, 2, 3, 4, 5, 6, 7, 8. So there are total 8 integers, positive integers which are strictly less than 30 and which are relatively prime to 30. And therefore, phi of 30 will be 8. So in particular, for if you take n equal to 1, so phi of 1 will be 1, phi of 2 equal to 1, phi of 3 will be 2. So phi of 3 will be again, so I'm phi of 4 will be 2. So what are the relatively prime integers which are strictly less than 4 and less than 4? So these are 1 and 3. So for 5 these are 1, 2, 3 and 4. You can check. Likewise for phi of 6. Phi of 6 there are only 3, 1 and 5. There are only two integers which are relatively prime to 6. So therefore phi of 6 is equal to 2, and you can check for 7. So for 7 these are 1, 2, 3, 4, 5 and 6. So total there are 6 integers which are already prime to 7 and less than 7. So as usual you can write one note: if p is prime number then phi of p will be p minus 1. So next, there are certain properties of this Euler's phi function. If p is prime and k is greater than 0, then what is phi of p raised to k? So it is nothing but p raised to k minus p raised to k minus 1, or p raised to k into 1 minus 1 upon p. So this one formula to calculate phi in terms of if n is given in powers of prime number. Again, the function phi is multiplicative function, means it satisfies this condition, that is phi of m into n is equal to phi of m into phi of n, where GCD of m and n equal to 1. So it satisfies this condition. So next, if the integer n is greater than 1, then what is phi of n? If you have prime factorization of phi n, then you will find phi n using this formula. So this is very important here. So use this theorem to calculate phi. See, if the integer n is greater than 1 has a prime factorization, that is n equal to p1 raised to k1, p2 raised to k2 up to pr raised to kr, then what is phi of n? Phi of n is given by p1 raised to k1 minus p1 raised to k1 k1 minus 1 into p2 raised to k2 minus p2 raised to k2 minus 1 up to, that is pr raised to kr minus pr raised to kr minus 1, or that is also equal to, so you can take p1 raised to k1 minus 1 common, or you can take p1 raised to k common, p2 raised to k2 common, pr raised to kr common from each term. So you'll get, so here p1 raised to k1 into p2 raised to k2 up to pr raised to kr, which is nothing but n, and what remains in each bracket, that is 1 minus 1 upon p1. In second bracket it will be 1 minus 1 upon p2 up to, in last bracket you will get 1 minus 1 upon pr. See, so in particular you can find phi of some integer. So let's find phi of 1001. So we have prime factorization of 1001. So you'll write it as 7 into 11 into 13. So here p1 is equal to 7, p2 is equal to 11 and p3 is equal to 13. Again, what is phi of p? Phi of p is equal to p minus 1. So we are directly using this formula, and you will get phi of 7 equal to 7 minus 1, phi of 11 equal to 11 minus 1, and phi of 13 equal to 13 minus 1. So you'll get 6 into 10 into 12, and that is equal to 720. So phi of 1001 will be 720. Similarly, you can find phi of 5040. So this is prime factorization of 5040. That is 2 raised to 4, 3 raised to square, 5 into 7. So you can take p1, p2, p3 and p4. What is p1? So P1 is 2, P2 is equal to 3, P3 is equal to 5, and P4 equal to 7. And you will take K1, that is 4, K2 2, K3, that is 1, and K4 1. See, so using this formula about theorem, so you'll get 5040, which is nothing but 540 into 1 minus half, 1 minus 1.3, 1 minus 1.5, 1 minus 1.7, and you'll get 504 equal to 1152. So again, you can find 5 of some integers. So 5 of 36,000, if you find it, you'll get 5 of 36,000 equal to 9,600. If you find 5 of 360, you'll get 5 of 360 equal to 96. And similarly, you can find this and check the answer. So next, there is Euler's theorem. What is statement of Euler's theorem? If n is positive integer and GCD of a and n is equal to 1, means surely, so n does not divide a, then a raised to 5 of n is congruent to 1 modulo n. So this is statement of Euler's theorem. See, if n is positive integer and GCD of a and n equal to 1, then a raised to 5 of n equal to 1, is congruent to 1 modulo n. So in particular, see, if you take, if n is prime number, then Euler's theorem reduces to Fermat's theorem. So in that case, if n is prime, then what is phi of p? Phi of p will be p minus 1. So you will get a raised to p minus 1 is congruent to 1 modulo p if n is prime number. So which is nothing but Fermat's theorem. Means Fermat's theorem is particular case of Euler's theorem, or Euler's theorem is generalization of Fermat's theorem. So find last two digits in the decimal representation of 3 raised to 256. So since GCD of 3 and 100, so we have to find decimal representation, last two digits in decimal representation of 3 raised to 256. So that's why we are taking here 100. If you ask last three digits, then you can take 1000 here. If you ask just last digit, then you can take 10 here, and likewise. So since GCD of 3 and 100 equal to 1, so using, or you can write 100 as 2 square into 5 square, that is its prime factorization. So therefore, what is pi of 100? So it will be 100 into 1 minus half into 1 minus 1.5. So you'll get 500 equal to 40. So using Euler's theorem, that is a raised to 5 of n will be congruent to 1 modulo n. So here it will be, so here we are putting, see, a is equal to 3 and n is equal to 100 in Euler's theorem. So you'll get 3 raised to 40 is congruent to 1 modulo 100. So let's call this equation as equation number 1. Also we have, see, 256, you can write 40 into 6 plus 16. If you divide 256 by 40, so then you will get remainder 16. So this is equation number 2. So hence from 1 and 2, what we can write? So you can write 3 raised to 256 as 3 raised to 40 into 6 plus 18, or which is congruent to 3 raised to 14 raised to 6 into 3 raised to 16. Actually this is equal to this modulo 100. Again 3 raised to 40 is congruent to 1 modulo 100 just from equation number 1. So this is nothing but 1 raised to 6 into 3 raised to 16 modulo 100. So 3 raised to 16 you will write 3 raised to 4 is power 4 modulo 100. 3 raised to 4 is nothing but 81. So 81 raised to 4 will be congruent to modulo 100. So 100 is congruent to, you can observe, minus 19 modulo, sorry. So just you can observe 81 is congruent to minus 19 modulo 100. See, so you can replace 81 by minus 19. So 81 raised to 4 is congruent to modulo 14. sorry, 81 raised to 4 is congruent to minus 19 modulo 100. So you can replace 81 by minus 19. So it will imply minus 19 raised to 4 modulo 100. See, so what is 19 square? So minus 19 square is equal to 361. So 361 is congruent to, again 361 is congruent to 61 modulo 100. You can observe. So using that, 361 square is congruent to 61 square modulo 100. Again 61 square is equal to 3721, and which is congruent to 21 modulo 100. See, 3721 is congruent to 21 modulo 100. So you'll get, see, 3 raised to 256 is congruent to 21 modulo 100. So what is that? So it means that 100 divides 3 raised to 256 minus 21, or using that definition of divisibility relation, so you'll get 3 raised to 256 equal to 100 into k plus 21, where cos sum k belongs to z, and therefore, so 21 is a remainder when 3 raised to 2056, sorry, 256 divided by 100. So what are the last two digits? So you can take any value of k. So last two digits will be 21, because if you take suppose k equal to 27, so what is 100 into 27? That is 27 2700, and plus 21 you will get 2721. So last two digits are 21. You can take any integer. Surely always last two digits will be 21. And this is about solution of this problem, and this is end of this course, that is number theory. So best of luck for your exam. If you have any query, you can call on 9767046000. So I will share MCQ questions in WhatsApp group soon. So we'll stop here.